All right, so here we go with our Chapter 5 study guide, which is all about probability. And I talked in the Chapter 1 study guide for my 2020 kids this year on the AP test. I think there will definitely be a question that makes you analyze a graph in some way. This chapter right here, probability, is another big thing that I believe will have a strong emphasis on your exam this year. Every single year, one of the 6 free response questions on the AP test is like focused on probability. And I think there will be a big chunk of one of your 2 problems this year that is over that concept. So definitely make sure as we're going through this that this probability stuff is coming back to you. It's been a while since we've practiced our more detailed rules, but overall, you guys tend to do pretty well with stuff from Chapter 5. It's just a matter of reminding yourself how to do it. So with that being said, let's go ahead and jump into our problems here. And our first example is looking at a two-way table and just asking us to find a probability related to that. They say that we are selecting one student at random out of this table, and we want to find the probability they take a bus to school. They don't specify what kind of student it's going to be. It's just one student out of the whole group. So that tells me my denominator then would be my 550. And then for my numerator, I would just pick the number of kids who walk. This is a pretty takes a bus, not walks. That's a pretty straightforward question, though. There are 107 people who took a bus. If you do 170 over 550, that equals 0.309, which is going to be choice B. So just a very straightforward calculate a probability out of a table. Moving on to our second question here. Using the same table, now it says if the student says he is a junior, what is the probability that he walks to school? As soon as you see that phrase, they're locking in junior on this problem. The student says they're a junior. We no longer care about the whole group anymore. We're not out of 550 like on number 1. Now, everybody who's not a junior doesn't matter to us anymore. We don't care about all those people, just this top row right here of everybody who's a junior. Well, out of that group of juniors, the probability you walk to school is going to be 48 kids who walk out of the 300 juniors altogether. And if you divide 48 divided by 300, that's about 0.16, which is choice B. So that is an example of a conditional probability. Junior was given in the problem. So that was the probability that we just calculated of walk given that they're a junior. And the given symbol is that vertical bar like I drew right there. So that also not terrible to do as long as you just look and if you look at the right part of the table. We got one more question using the same table here. So let me clean up a little bit of this marker. And for this last question, they're using 2 vocabulary terms you guys should be pretty familiar with. The first one is mutually exclusive, and the second one is independence. So in order for 2 events to be mutually exclusive, our 2 events are walks to school and junior. If those events are mutually exclusive, it means they cannot occur at the same time. It's impossible to be both of those things and have both of them at the same time. You can totally be a junior who walks to school. And the way I'd verify that in the table is I would look junior and walk. If it was mutually exclusive, I would see a 0 right there, but I see a 48. So these events are not going to be mutually exclusive. So I can cross off all my choices that say that they are mutually exclusive. If they have overlap, it's not going to be mutually exclusive. So we're down to 2 choices there. We have B and we have D left. And B and D talk about the concept of independence. Now, we have a conceptual way that we explain independence, that being that one event doesn't give us any information about the other. But there is a mathematical way you need to check and verify whether 2 things are actually independent. The formula we learned way back when, you would take the probability of A being whatever my first event is, and I would see if that's the same as the probability of A given B. Or I could reverse the A's and B's in my little formula right here. These 2 probabilities being equal is how you establish independence. What does that mean? It means that if B happens, B is given in the formula, it doesn't change the probability of A. So what I would need to do to verify independence in this problem is instead of doing A and B, I'll go ahead and change this to the problem. They're talking about walking to school and being a junior. It doesn't matter which one I do first. So I'm just going to go probability of walk. So I would compare probability walk to probability of walk given junior, and I need to see if those two things are the same. So if you look at the table up ahead, probability you walk is just 88 out of 550. So I would have that for my first one, 88 over 550. And then for my second one, I have to do probability of walk given junior. I believe that's one I already figured out. Was that the last question? Yeah, that's exactly what I found out in the last question. Walk given junior is 48 out of 300, which is a 0.16. So if you make decimals for both of these, they actually are equal to one another. Both of these, if you divide them out and solve them, are 0.16. So that means if we know somebody's a junior, it doesn't change the probability that they walk to school. In other words, junior tells us nothing about walk, and they are actually independent. So you need to verify the conditional probabilities. If they're the same, the events are independent. So this is not mutually exclusive, but it is independent. Correct answer to this one is B. So we're moving right along here to our second page of multiple choice. And for this problem, we've got a kid who needs to get to the bus stop. If he makes it by 7:30, there's a 15% chance that he misses the bus. So we're looking at 3 days in a row, assuming independence, and we want to figure out the probability he catches the bus each day. Well, if there is a 15% chance he misses the bus, that means the complement of that, there's an 85% chance he does catch the bus. And he needs to catch that bus 3 days in a row. When you're doing probability, or probability means you add them together and then you subtract the overlap if there is any. This is and, though, because I need the first day and the second day and the third day. So I need to multiply makes it and makes it and makes it again. And if I multiply 0.85 to the third power, that equals 0.614, which is choice D. So next problem. The probability you win a prize in this lottery is 11%. Given the nature of lotteries, it's independent, good. If it wasn't independent, we couldn't just straight up multiply them. So that's just a little disclaimer. These problems we'll always have. If you buy one ticket each month for 5 months, what is the probability you will win at least one prize? So this problem right here is actually binomial. That's a chapter 6 topic, but we'll talk about that next time. You could solve this problem using a binomial setup. But if it says at least one, what that should do in terms of chapter 5 probability is signal to you complement. It's probably easier to find the complement when they ask you a question like this. So the complement of winning at least one prize means you win no prizes at all. And it's actually easier to find the probability you don't win any prizes and then just do a 1 minus on that. Because if you did at least one prize, you have to figure out probability of exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, and add all those up. Big mess. Way easier just to find probability of no prizes and do the complements. So if me winning a prize is 11%, me not getting a prize is 89%. I would need to not get prizes 5 months in a row. So that would be, I can just do a fifth power instead of multiplying it out like last time. So that would be the probability of me not winning any prizes. But I want at least one prize, which is the complement of that. If you do a 1 minus on this guy, that equals about 0.441, which is choice C. One more multiple choice question to go. So for this problem here, we've got a sit-down restaurant, blah, 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 tables with children or not, and then people ordering milk or not. Our two big tools in this chapter, when you're talking about probability, making a table and making a tree diagram. So one of those two strategies can usually help you if you're dealing with a more complicated probability question, tables and tree diagrams. If there's a sequence to the events or you have conditional probabilities, tree diagrams are the way to go. And the first thing they talk about in this problem is, hey, 40% of tables have children. And then that means 60% would not. And from there, it talks about, oh, how likely are you to order milk? So 40% of tables have kids at them, so 60% don't. Of the tables with children, the rate at which people buy milk is in 30% of orders, meaning that 70% would not. So that's going to be no milk, And then in the no children tables, only 10% of people buy milk, because that'd be a little weird. No offense if you enjoy a milk with your restaurant meal. And then 90% of people without children do not get milk. So this is our little setup. It's a good idea to set up a tree diagram when you tackle a tougher probability question. Next thing I'm going to do is decipher what they actually want me to find. And they are looking in this problem for the probability of children given milk. That word given should signal to you that it's going to be a conditional probability. Children given milk is what we're looking for. So, conditional probabilities. Sometimes you can use common sense, like that junior walking problem where you just covered up the part of the table you didn't want. In a tree diagram, it's not always that easy, because if milk is given, that's not the first thing in my tree. So this isn't very easy to figure out just by looking at this. You have to use the conditional probability formula. And what the conditional probability formula says, C given M, it's the probability of both. That would be C and M, using my intersection symbol there. So C and M over the probability of the one that's given. So I would have to define the probability of both over the probability of milk. In order to do that, I need to multiply out my branches. So like I would go 0.4 and 0.3. This branch is at 0.12. 0.4 times 0.7 is 0.28. Then I have 0.06, and I have 0.54. So I just multiplied out my little probabilities here. And now I'm ready to find my answer. The probability of children and milk is going to be this branch right here. Children and milk is this guy. So my numerator, I'm going to put it like over on the side, is a 0.12. I just did 0.4 times 0.3. That's children, that's milk. 0.12 is this top guy right here. The bottom guy is the probability of milk. Well, that could happen with my green path, but it could also happen with this path right here. No children and milk as well. So for my probability of milk, I have to add those two together. So I would have 0.12 and 0.06. You could very easily make that a 0.18 right away, and that would be okay. But showing extra work is a smart idea when you can. If you divide those, you're going to get 2/3 or 0.67 for the answer. So we had to use our conditional probability formula to correctly solve that one. Okay, so I hope you've taken the time to try these problems out. You're not just watching me do them. Try them for yourself first, especially this free response question right here. It's kind of a lot to sift through. This is a question that's a little bit tougher just because you have to wrap your head around what this ELISA, whatever it's called, test is, and this HIV situation with the blood samples. There's really a lot going on in this problem. So make sure you read it to yourself. Anytime you tackle a probability question, ask yourself, can a table or a tree help me out? And in this problem, it looks like what we've got going on is we've got 500 samples of blood that have HIV. So if you look at like this second sentence, right, or this guy right here, 500 samples have HIV, and then it talks about positive and negative rates, and it talks about 500 samples that don't have HIV. So this is going to be a great question for a little two-way table. It's going to help us organize our problem. So what we've got going on is we've got the blood samples that have HIV, and then we've got the blood samples that do not have HIV. So no HIV. Whew. All right. So I've got that going on. And then the other thing I care about is whether this ELISA test comes back positive or negative. Positive means it says, yeah, you've got HIV. Negative means it says no. So we have 500 samples for each problem here. 500 samples with, 500 samples without. And then in the problem, it just tells us what the breakdown is. Apparently, out of the HIV group, 489 people or blood samples with HIV. Oh, that was so bad. 489 people out of the HIV group are correctly diagnosed as being positive. That's a good thing. That's what's supposed to happen. There are 11 people who slipped through the cracks and tests said they were negative when they were actually positive. In the no HIV, 37 were incorrectly told, oh yeah, you've got a positive test. And then there were 463 who were correctly diagnosed as negative. And if I get my totals going on over here, there's going to be a 526, And then this guy below it is 474. So a lot of setup here, especially painfully watching me write this out, but it is helpful to have all of your numbers organized. Now let's read the problem. Using the data from the program, estimate the probability that the test would be positive when it is applied to a blood sample that does not contain HIV. That right there, does not contain HIV, is a hidden conditional probability. What they're really asking us for here is the probability that you get a positive test given that you have no HIV. So if it's given that you have no HIV in a table problem, these are lovely questions. All you're going to do is cover up the part of the table you don't want. And I don't want to ruin my table with purple ink here, but no HIV is going to be this second right column. There are 500 people who don't have HIV, so that is my new denominator instead of the 1,000 total. And then I have a positive test 37 of those times. 37 over 500 is going to be a 0.074. Make sure you're showing some sort of work. This is going to be tough typing in yourselves here, so you can make a little table or just show work in some fashion when you answer that question. Okay? Pretty straightforward question once we got ourselves a table. Second problem, among blood samples examined in the training program that provided positive results, what proportion actually contained HIV? This is another not very difficult conditional probability question once you parse through what it's trying to say. This time, we know that the test was going to be positive. So given positive, what's the probability that they actually contained HIV? So still no need for crazy formulas. When you have a table, you just cover up what you're not caring about. And I need to cover up this bottom row right here, the negatives. Only look at the positives. So I'm out of 526 for this problem. That's the number of total positive tests. And then I have 489 that actually tested positive. Sorry, that actually have HIV. So I have 489 HIV out of the positive tests. And if you divide those out, you should end up getting 0.930. So these first two questions here, honestly, smooth sailing as soon as you read through the problem and figure out what they're even trying to do. Because it is a weird setup, but then they're not that hard. Part C is a bit crazy with everything that's going on. So let me try to break down in my own words what this last one is saying. What they're going to do is they're going to look at a test sample of blood. If a test sample comes back positive for HIV, what they do is they don't automatically assume you have HIV right there. They want to follow up with more tests to be certain, or be more certain anyway. So as soon as you get a positive test, what you do is you get sent on and you take 2 more tests no matter what. So you take your first test, that's like a red flag. Oh, positive test. Then you take 2 more tests. Okay, so you've now taken the test 3 times total. If either of those 2 new tests is positive, they send you off to the fancy laboratory to get even more testing done. If both of the new tests come back negative, they assume that first positive was just a false positive and not a big deal. So that's what's basically going on in terms of the setup. It's a lot to wrap your head around when you read that paragraph. So what I need to do with this problem right here, we're talking about, a positive test or negative test, and I send it on and I don't. This is definitely a tree diagram. Always be thinking for yourself, how can I make this problem easier with a picture? And what we look at first in this problem, this set of blood that we're analyzing, we're looking at a set of blood that does not contain HIV. There is no HIV in this blood that is given in the problem. Okay. And really each time we do a test. So this is me walking in the lab. Oh, my blood doesn't have HIV. I'm going to take a test. The probability that it will come back negative, we actually calculated it back in part A. Probability questions love to do this, where they grab an answer from an earlier part of the question and make you use it again. So if you're doing a big probability question in general, always look to see if you've done the work before you start to do it again. They usually kind of push you or guide you along a path and use your answers repeatedly. So part A was exactly that, getting a positive test when you don't have HIV. So that sample of blood has no HIV. The probability of getting a positive test is 0.074. That means the probability you get a negative test like you're supposed to, if you don't have that, is the complement, which is what? 0.926. And if I get a negative test, I'm good. Like they're not going to test me anymore. I'm just like happy. Oh yeah, I'm cool. So this part of the tree doesn't really matter to us anymore. That doesn't really do anything. If we get that first positive test, I'm going to switch color here for making it easier to distinguish. So I got a positive test. I'm not automatically like going to be freaking out just yet. I have to take 2 more tests no matter what. So as soon as I get my first positive, I am going to go take 2 more tests. Or my blood is going to be tested 2 more times. And then the probabilities for these, it says that the tests are assumed to be independent. So every plus is going to be a 0.074 in this problem. And every minus is going to be a 0.926. So I've got this going on right here, got myself 0.926, et cetera, et cetera, et cetera. Now, as I'm finishing writing these on here, the problem says that we need to figure out the probability that a sample without HIV gets sent to this more expensive test. You get sent to the more expensive test if you get positive at least 1 time in this setup. So let's talk about what that means now that my picture is finally labeled. So if my blood comes back negative in the first place, I'm done. Nothing else going on. If it comes back positive, I automatically do 2 tests. So this path right here, if my blood shows up positive all 3 times, I am definitely going to get my blood sent on to the more fancy testing that's beyond the problems. They send us to the new fancy lab. If I have at least 1 positive, so if I get my initial positive, sends me to the green area, then I get a positive and a negative. If you get at least 1 positive in the new stuff, you got to get the testing. So they're sending me onto the fancier lab. And then one more time, if this test is negative, but the next test is positive, that would also send me to the fancier lab. The only way I would not go to the fancier lab if I go to the 2 new tests is this last path I didn't highlight where they both come back negative. Then it would be assumed that my first test was just a mistake. So I'm not going to make you guys watch me write this all out on here, but what I would do is I would multiply each of these paths, boom, 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 and I would add all 3 of those answers together. If this was your test, show your work. 0.074 times 0.074 times 0.074 plus this and add them up. If you do that, though, it's still a really low answer. It's going to be 0.0105. And then you would just write like a little sentence in context. The probability that a test without HIV goes to the fancier lab is that. Okay? So tree diagrams make our lives a lot easier once you actually have them set up. They're a really good tool to use in probability questions.